All right. So okay. So let us look at few problems about spins. Okay. So I have collected few questions which I think is conceptually important, and I think you will like this. Okay. So this will make your concepts even stronger. Okay, so the first question is, after doing a rotation about z-axis by this phi amount, so what is the form of the Sx, Sy and Sz? Okay, so as you know that this rotation is actually a unitary transformation, right? So under unitary transformations, uh, the states change, right, by unitary transformation, and also the operators change their form. Okay, so the question is, if we do this kind of unitary transformation, which is physically a rotation, so what will be the form of Sx, Sy and Sz? Okay, so let's try to work it out. So okay, so I have a rotation operator. Okay, so rotation operator is given by, so let me write it like this. Okay, so some problem, my screen broadcasting stopped. Okay, by the way, is my video and audio is okay? uh, yeah, so let me just share my screen back. I had some problem, it's just stopped suddenly. All right, so let's begin, right? Yeah, yeah, go on, Shagnik. Yeah, yeah, best, yeah, best six, right? So in case you are right, so in case you are submitting 8 assignments, so let's say you will have some marks, right? So they will sort out the best of those 8, and they will consider only 6 for your certification. Okay. Okay. Okay, but you have submitted the assignment though. Okay. Okay, that's fine. That's fine. That's fine. But yeah, that's I think that's okay. 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 So let us come back to rotation. So we are talking about rotating a spin. Okay. So I mean, for spin rotations, the operator is given by, let me write it like this. So d uh, z phi. Okay, so I am considering a rotation about the z-axis by amount phi. So this is, as you have seen in the lecture, this is given by a unitary operator, which is just this, sz phi by h bar. Okay, so now this is a unitary transformation, right? So I mean, any physical transformations which you can do on quantum mechanics is basically unitary transformations. So unitary transformations are transformations which keeps your probability same. Okay, so it keeps the, let's say, the length of this k vectors same. Okay, so this is this kind of transformation. So now the question is, so if this is my transformation, so what happens to, how does this Sx looks like? Okay, so now if I do this operation on Sx, then what I'll do is I'll sandwich the Sx between these operators, right? So I'll act minus Isz phi h bar and Isz phi h bar from this side. Okay, so this is how the operators change under this unitary transformation. You have to apply from both sides. So unlike states, so how does states change? So if there is a state, if you want to rotate it, you just apply it from the left hand side. Okay, but for operators, you have to actually sandwich them from both of the sides. So now we have to calculate this operator. So this is what has been asked in the question. So can we simplify this a little further? Okay, so answer to that is we can actually. So there are basically two methods. Okay, so first of all, let's consider a form of this S matrices. Okay, so let's consider that we are talking about spin half. Okay, so if we are talking about spin half, then the Sx has this particular structure. So Sx is written in terms of h bar by 2, and there are plus minus, plus, minus, and plus. Okay, and so I am writing the Sx operator in terms of the eigenstates of the Sz Hamiltonian. Okay, so because the Sz is a operator which I am considering to simultaneously commute with our Hamiltonian or simultaneously commute with s square. Okay, so just to make it concrete, so Sz plus acting on plus gives you plus h bar by 2 is plus, and Sz acting on minus kate gives you minus h bar by 2 and minus. Okay, so this operator Sx you can write in terms of this Sz. Okay, so now when you have done this, so there are particular reasons why you should do that, because that will make the math a lot simpler. So let's just take this S and let's apply the e to the power this rotation operator basically on it. Okay, so it is Sz phi h bar Sx e to the power minus I Sz phi h bar. Okay, so let me put this form of Sx which I have chosen. And inside the bracket there is plus and minus kate, brass and kates, plus, minus, and plus. Okay, and there is additional Sz phi h. Okay, so now you can actually apply these operators on this projections. Okay, so e to the power I Sz phi by h bar plus minus e to the power minus I Sz phi h bar and plus h bar by 2 So now when you are done with that, let's consider the action of this Sz on this kate and action of this on this bra. Okay, so what will happen is, because the Sz's these are plus and minus are just the eigenvectors of Sz, so that's why when you will apply these operators it will just become e to the power I. So let's say, so this is plus, so I'll use h bar by 2 phi times 1 by h bar. Okay, so h bar and h bar cancels, so I am getting e to the power I phi from the left hand side, and similarly it will become it will also become plus phi by 2. Okay, so similarly you do for the other terms, you will get minus I phi by 2 minus plus e to the power minus I phi by 2. So the thing it boils down is just it is e to the power I phi plus kate minus and plus is minus I phi and minus and plus. Okay, so if at any point if you have any question, please ask me. Okay, so now we can just write this e to the power I thetas I phi's in terms of cosine and sines. So cos phi plus I sin phi plus and minus plus cos phi minus I sin phi minus and plus. So I can collect things, right? So I can collect things, I can make it like, so cos phi plus minus and plus minus plus. So I have taken cosine common, okay, from these two terms, and additionally I can take so let's take minus sine, let's say I sine minus plus and minus plus minus. Okay, so now if we recombine all of these things, so this becomes cos phi Sx. Okay, so this part, so basically this is again my Sx, right? So h bar time h bar by 2 times this part is basically my Sx. Okay, so I am writing Sx, and I can and the rest of the part is actually Sy. So Sy will be given in terms of minus h bar by 2 I plus minus and minus minus plus. So this is the form of sy. Okay, so now, so see what we have done. So we have actually started from s(x), we have rotated it with respect to the z axis. Okay, so my s(x) operator after rotation about z axis. Okay, so it became something like this cosine of phi s(x) minus sine phi sy. Okay, so similarly you can actually also do for sy also. Okay, so sy, you will find out the sy will become something like in the same set of calculation, you will find out it becomes something like sine phi s(x) plus cos phi sy. Okay, and sy, if you will do that, you will see that sy actually doesn't change at all. So why it will not change? Because we are just rotating about the z axis, right? So whichever axis we are rotating about, so that quantity doesn't change, but all of the other quantity which is not on the same axis, then all of those will actually change. Okay, so what does this actually mean? So I guess you have learned about vectors and how do they rotate. Okay, so let's look at that thing once. So let's say I have a vector r. Okay, and I have a rotation matrix given by r. Okay, so this is the matrix, and so let's call this r prime. So I have initially I have a r vector, so then I am rotating it, and then I am getting a r prime vector. Okay, so these rotations, like let's say for the rotations about the z axis by this amount phi, you can write it in terms of cosine phi minus sine phi cosine phi 0 0 1 0 0. So this is how you write the rotation matrix. So you apply this rotation matrix to this vector. Okay, so let's consider that my r is given in terms of x, y and z. Okay, so just it is, let's say it is a position vector. Okay, and I am rotating it. So now so x prime, y prime and z prime will be given in terms of this thetas, where you have to apply the rotation matrix on x, y and z. And we're applying it on x, y, z. So if you do that, you will see that you are getting the same equations again. So you will get x prime is equal to cosine phi x minus sine phi y. Okay, so look at the similarity between this equation, like this one and this one. Okay, so don't they look exactly same? So the thing is so if we have so let me give you the general statement. So if we have a spin, okay, so here the spin is actually an operator also. So spin has three components. Now if you do the rotation, okay, so for even if we are rotating, so the rotation will change the spins by the same way as you do for a classical vector, like as I have shown you for this position vector. Okay, so this is actually, this holds generally. Okay, so let's say I am writing it in terms of the expectation. So you take expectation and you just rotate it like you do your classical vector. Okay, so this is actually very deep connection to this rotation. Okay, so even if our rotation, so like as I've shown you that the rotation is given by this kind of a weird looking object, the effect of this on the operator is nothing but the effect, how the effect of rotation is on a classical vector. Okay, so yeah, so this is how it is. Okay, so this is one way. So in this way we have actually chosen a form of this s(x) operator. So we have chosen that, okay, this is actually spin half Hamiltonian. So this is a spin half that we are talking about, and we can write the s(x) in terms of the eigenstates of sz. Okay, so that's what we have assumed, but we can also do this for a general case also. The general case I will show you. So but before that, let me ask, is there any question, any confusion regarding the steps?
Hello, sir.
Yeah, go on.
Sir, actually, I have checked the week 3 assignment. Sir,
B3, week 3, right? Yeah, yeah.
yes, sir. Sir, in week 3 assignments, the questions are from
Week 4.
week 5 actually.
Yeah, week 4 and week 5, right? Yeah. So yeah, so you have to watch week 4. Okay, so if you watch week 4, then you will be able to do some of the assignments. So I don't know what to say about it. So yeah, so I have chosen these spin problems because this for the week 3 it was mainly on spins in angular momentums. Okay, so that's why I'm focusing on this set of problems which concern angular momentum and spin momentum. Okay, so that's why we have been doing this. Okay, so I guess this is okay. So now let me show you a general way so that we don't have to assume any spin. We don't have to assume any spins matrix. Okay, operator. So how do you go about it? So we want to calculate something like this. So let me first show you there is a identity. There is a formula which is called Baker-Campbell-Hausdorff formula. Okay, so this is widely used in quantum mechanics. So let me show you what this thing is. So let's say I have some operator e to the power ia b e to the power minus ib ia. Okay, so all of these are operators. Okay, now so you can expand those exponentials, and because in quantum mechanics these are operators and these do not commute, so so you will get some set of commutators. Okay, so now if you do this algebra, you will see that this becomes something like this: I a comma b is commutator plus I square by 2 factorial a comma b. It's a commutator inside a commutator. So if you go on, you kind of see the pattern, right? So it becomes like the same repeating commutator structures. Okay, so it is actually infinite. It is actually an infinite series, but this is a very useful thing to prove theorems, to prove formulas in a general setting. Okay, you don't have to assume a lot. So what you want to calculate is, when to calculate e to the power minus e to the power I phi. Okay, so s z phi by h bar sx e to the power minus I s z phi by h bar. Okay, so now what you can do is you can just use this BCH formula, Baker-Campbell-Hausdorff formula, and you can just write this set of commutators. So the first one becomes sz comma sx, second one becomes okay, so there will be phi by h bar. Okay, so these are the constants which will be there. So I phi by h bar square 1 by 2 factorial sz comma sz sx commutator, and so on and so forth. Okay, so if you write all of this and if you use the commutation relations, what are those? So those are just sx so you will, for here you will need like si sj. The commutation is given by I epsilon I j k sk. Okay, so where this I, j and k, this belongs to x, y and z, so this runs over x, y and z, and this is the Levi-Civita. Okay, okay, so you have to use these commutation relations. Now if you use these commutation relations, and you will find that this will again give you sx cos phi minus sy sin phi. Okay, so this is a bit of algebra, so I'll ask you to do that algebra. So after doing that algebra, you will see that this becomes again same. But here you see we have not assumed any spin. Okay, we are saying that we have these spin operators, and this derivation is actually valid for any spins, okay, or any angular momentum kind of operators. So this is the general thing which you can also solve this kind of problem. Okay, so is this any question up to this point? All right, so okay, so let us look at yeah, so let us look at this case. Okay, so we have now seen that what happens to these spin operators sx, sy and sz upon rotation. Now let's look at what happens at the states. Okay, if you rotate it. Okay, so you will see that there is a very weird thing which comes out of this rotation of the states. Okay, so okay, so the problem 2 is rotate a general kate. Okay, so I'm assuming that this is the case of spin half. So I am writing this in terms of the completeness relation. Okay, so the completeness relation is given by let's say n and alpha. Okay, so the completeness relation I'm using is this n are the eigenstates of the sz operator. So n is identity. Okay, so this is nothing but the plus and minus this thing which I was talking about in the last problem. So I'll be using that. So now this thing becomes plus and minus. So why do I keep trying to go to this always the basis of the sz? So because this is helpful because we are considering a rotation which is of the form e to the power minus iz phi by h bar, and it is actually helpful to consider the state in terms of the states of this sz operator only. Okay, so that way calculations become a lot more easier. Okay, because these obey the eigenvalue equation, so calculations will become a lot easier if we expand the eigenkate in terms of this plus and minus eigen states of the spin operator. Okay, of the sz operator. So minus alpha. Okay, so this is my alpha when I have written in terms of this plus and minus states. Okay, so I have my alpha, then I will do this rotation. So rotation will take it to some alpha prime, let's say, so which is given by e to the power minus I sz phi h bar and alpha. Okay, so let's just write the state. Okay, phi plus alpha plus minus alpha. Okay, so as you might remember that this plus is the eigenstate of sz with plus half, and minus is the eigenstate of sz with minus h bar by 2. So we will just use the fact and we will just write minus I and phi by 2 plus alpha plus e to the power I phi by 2 and minus alpha. So see, what I have done here is I have just used the eigenvalue equations of sz and I have converted. So I have just put in h bar by 2, so h bar from numerator and denominator cancels and I am only left with minus I phi by 2, and here I am left with I plus I phi by 2. Okay, so now this is how the state rotates. Okay, so this is the unitary transformation upon the state. Okay, this is how it rotates. So now from our normal classical thinking, so what we know that, so let's say we have some object. Okay, so now let's rotate it 360 degree. Okay, let's say that I am rotating it around this axis, 360 degree rotation. So what happens is all of the things actually come back to the same place. Okay, right? So because 360 rotation means 2 pi, it doesn't change anything. Okay, so the object should come back to itself. This is the normal thinking. Okay, but here this is not true anymore. So because of this this phi by 2s and phi by 2, we see that upon doing a 360 degree rotation, it doesn't come back to itself. So let's just do that. So let's say that my phi is 2 pi, okay, which is again 360 degree. So if phi is 2 pi, then the alpha prime will be e to the power minus I pi and plus e to the power minus e to the power plus I pi. Okay, so I am just putting phi as 2 pi. So 2 from numerator and denominator cancels and I am only left with this. So you know that e to the power minus I phi is nothing but minus 1, right? So I will take the minus 1 common and I will write the rest of the part. So this is nothing but my alpha, right? So which the state which I started with. So we see that when we are doing a 360 degree rotation on this state, right, on an arbitrary spin half state, so it doesn't actually give it back. So it only changes its sign. Okay, but even if it changes sign, if we were to calculate any expectations, okay, then you see the minus from both of the sides, so this will give a minus and this will give a minus, so minus will become plus, right? So for expectation values it doesn't matter, okay, but the states actually get a minus sign upon a 2 pi rotation, okay. So so when does it come back to itself actually? So after not 360 degree, okay, not after 360, it comes back to itself after 720 degrees, so twice, so 4 pi rotation, okay. So when you do a 4 pi rotation, you will see that you will get the correct sign, get the plus sign. So this is kind of weird, right? So this happens in spin half systems, okay. When you will rotate it by 2 pi, it doesn't actually come back to itself. So this is a really weird phenomena, happens only in quantum mechanics, okay. So is this point clear? So any questions, any doubts, please feel free to ask. Yeah.
Sir, means for spin 0, 1, 2 means integral spin system like boson.
Yeah. Yeah.
Now, foreign property will be different, right?
So so yeah, that is a good point that you are trying to make. So for bosonic operators, so operators, the rotation operator will be exactly same, okay. So like I S Z phi by h bar, okay. But for bosonic case, so the SZ will be some larger kind of matrix. So let's say you have, so it is always of 2s plus 1 times 2s plus 1, okay. So you will always get this 2 plus 1 by 2 plus 1 dimensional matrices, so which will be different, right? So for spin half we get some set of Sx, Sy and Sz, but for interior spins we will not get same set of matrices, we will get something different, okay. And in that case you will actually find out, so this phi by 2 which appears for this fermionic case, like these are the spin half particles, right? So for spin half particles, this fractional things actually appears only here, but for bosonic things you will not have this problem. So for bosons, when you go for 2 pi, the state will come back to itself, okay. So is that clear, Sharinga, or you are making another comment about it?
No, sir. Means yeah, that I know that it will come up. It will come to the same state after 2 pi.
Yeah.
That's what I'm asking, sir. Equation, this equation, sir, to the power minus 5 by 2.
Yeah.
Change, right?
Yeah, this will change. Yeah, so you'll not have these half factors. For bosonic case, you'll not have these half factors. So that's why there will be no problem. Okay. Yeah. So to solve that, you will have to construct these matrices explicitly, and you'll have to solve eigenvalue problem. Then you can come back to, you can ask the same question. You can ask, okay, so if my alpha is for a boson, okay. So let's say boson of spin S. So then what will happen? So to see that, you will have to do the same steps, but this operators will become different. Okay, operators will become different, so you will get a different result. Okay, which will not have this kind of this problem like fermions have. Okay, so let's move on to the next one. Okay, where was I? Okay, so yeah, so similar thing. So I'll just show you how to do one for one, so you can do for the rest. Okay. So now, so this is the problem of spin precession. Okay, so which is a I mean historically very well development of, so how the spin actually precesses. Okay, so this is the precessing motion of spins. So now let's say you are given a Hamiltonian like this. Okay, H is given by omega Sz. Okay, so now someone is asking you to calculate the time dependence of these expectation values. Okay, so how do you go about it? So like this, so when you write like the Sxt, right? So Sxt will be given in terms of this this is the Heisenberg operator, right? So which will be given in terms of e to the power IH t by h bar Sx and e to the power minus I h t by h bar. Okay, so now the Hamiltonian, so let's put the Hamiltonian. So this becomes I omega Sz t by h bar, and this becomes e to the power minus I omega Sz t by h bar. Okay, so you see that this exactly looks like the last problem we did. Okay, so last problem, how we rotate the operators. So this is exactly same, but here my phi is given in terms of this omega t by h bar. Okay, so this is what the phi is. Okay, so you can do the same algebra like you have done before. So like I have shown you, you can do the same algebra and you can find all of these time dependencies. Okay, so I will directly show you the result. So if you do this algebra, you will find out that xt is given in terms of sx cos omega t minus sy sine omega t. So I am doing nothing, I am just replacing the phi's by this omega t. I think I have missed some h bar also, so let's put at some h bar here. Yeah, probably that would be okay. So then phi becomes just omega t. Okay, so you can just do the problem and you can try to see for yourself what do you get. Okay, so this is just using the same trick that that we have discussed in the first problem. So yeah, okay, so let's look at something else. Yeah, so let's look at this. So this is a general kind of rotation operator. Okay, so in this problem, so we are looking at a general rotation operator. So that means on around some n cap direction, I'll do rotation about phi. Okay, so there is the n cap direction in my 3D space, and about that I'll do some rotation phi, and this is the operator that does that. Okay, so we can actually expand it, we can actually simplify it even more, this operator. So so how to do that? So to do that, first let's use the Pauli matrices. Okay, so we'll be using the Pauli matrices algebra. So the spin is given in terms of Pauli matrices like this. Okay, so this is I mean, this is how the spin is represented in terms of Pauli matrices. So then in terms of Pauli matrices, my rotation operator, it becomes minus I sigma dot n cap phi by 2. Okay, so yeah, so this is it. So now you know this how to expand exponential e to the power x. So e to the power x has a Taylor series which is given by x to the power n by n factorial, right? So for matrices also it means the same. So you can expand it, you can write like sigma dot n cap by 2 plus, okay, so there is I have missed one I, and minus I, and there is plus I by 2. So okay, so I okay, so let's write it together, sigma dot n I by 2 whole square 1 by 2 factorial, and so on and so forth. So you get the point. So we have to expand it in terms of this like how you expand the Taylor series. Okay, so now there is a very nice property of Pauli matrices which you have to use. So like if you get this kind of combination sigma n to the power n, right, so which you will get in this Taylor series, so this will become 1 if n is even. Okay, so this will save you a lot of work. So this will become sigma dot n if n is odd. Okay, so you can clearly see from here, like this will become sigma dot n part, this will become 1. Okay, so this will remain. So like the cubic term will also give rise to sigma dot n. So all of the odd terms will you can keep it as sigma dot n. Okay, so if you'll do that, at the end of the day you'll be able to resum this series. Okay, resum this series in terms of sines and cosines. So if you resum this thing, so it will become cos of phi identity, and minus, okay, yeah, minus I sigma dot n and sine phi. So this is the thing that you will get. Okay, so probably this is okay. So I missed this half. So cos by sine by 2 and sine by 2. Yeah, so you have to resum the series again, then only you'll be able to get this thing. Okay, so this is a good exercise. I mean so you can have some practice with the matrix algebra or Pauli matrices. Okay, so you can do that. You can do this kind of algebra. This is pretty simple. Okay, it is a little bit long, but it is basically very simple. So is this okay, or do you need me to explain again? All right. So let's move on to the next one. So yeah, so Pauli matrices has very nice properties. So let me demonstrate another nice property to you. Okay, so now say you have given a Hamiltonian like this. Okay, so this is a two-level system. So this is called a two-level system, and the Hamiltonian for this is given by h is equal to epsilon sigma dot n cap, and this n cap is any arbitrary unit vector. So now you are asked to calculate the eigenvalues of this Hamiltonian, right? Because when you are given a Hamiltonian, you are always interested to find the eigenvalues. So how do you go about it? So there is a longer way and there is a smart way. So the longer way is, so let me first try to give you some hints about the longer way. So sigma vector, this means that sigma x I cap plus sigma y j cap plus sigma z k cap. Okay, and so the n cap, so we are thinking in terms of let's say this polar coordinates. Okay, so polar coordinate, this n cap you can write like, so how you can write this n cap? So n cap will be your some x cap. Okay, so n cap, let's write the n cap properly. So this is my phi and this is my theta, and let's say this is my n cap direction. Okay, so n cap for n cap direction, so this is my x, y and z axis. So this will become sine theta cos phi I cap plus so y thing will be sine theta sine phi j cap and cos theta k cap. Okay, so you can use that n cap. Okay, so which will give you basically epsilon sigma x nx plus sigma y ny plus sigma z nz. Okay, so this is what I am calling as this is my nx, this is my ny, and this is my nz. Okay, so this so you can write this in the matrix forms of this. So the first term becomes 0, nx 0. So in terms of, in place of nx, you will place the sine theta and cos phi, and then you are left with this 0 minus I ny 0 plus nz 0 0 minus nz. Okay, so basically you get a 2 cross 2 matrix, right? So let's write the 2 cross 2 matrix. So this is nz nx minus I ny and nx plus I ny and minus nz. So basically what you have to do is you have to put all of the values of nx, ny and nz, and you can basically get the eigenvalue, eigenvectors, right? This is a 2 cross 2 matrix. This will not be that difficult, but there is an even smarter way to do this. Okay, so to do that, let's first start with the Hamiltonian again. So Hamiltonian is epsilon sigma sigma dot n cap. Okay, so now let's take a square. Okay, so h square will becomes epsilon square sigma dot n whole square. So like in the last problem, we have used the property whenever there is an even power of sigma dot n, this is basically 1. Okay, so h square becomes epsilon square. Okay, so then you can use something called the Cayley-Hamiltonian theorem. So what does Cayley-Hamiltonian theorem say? Is that Cayley-Hamilton's theorem says that whenever there is a power of the matrix for which you are taking the eigenvalue, you can basically replace that Hamiltonian matrix's power with its eigenvalues. Okay, so let's say that I am saying that my Hamilton's eigenvalue is E, so I am just replacing the h square by E square. So that is the Cayley-Hamiltonian theorem, so which is given by E square. Okay, so my energy is now just plus minus E. Okay, so I have not done any complicated algebra here. I have just done a square on both of the sides. Okay, so for this example, so the energies are given by minus epsilon and plus epsilon. So this is a two level problem, two level system. Okay, so that's like using the simple algebraic properties of the Pauli matrices, you can do a lot. Okay, you can do a lot with a very little bit algebra. Okay, so I hope this is clear. So let's move on to the next one. Where was I? Okay, all right, so let's look at this problem. Yeah, this one. So at any point if you have any doubt, so please ask me. Okay, yeah, please. Yeah, okay. Yeah, this is recorded and you will have the link to this video. Okay, I think so there is a section in the course website which is called I don't know, so there is some section where all of the recordings are there in a spreadsheet, so which is stored in a week by week manner, so you can look back again. Okay, so these are recorded. Okay, all right, so okay, so let's look at this Hamiltonian. Okay, so this looks fair bit of complicated, right? So this is a spin 3/2 Hamiltonian. Okay, and so now I am asking you to calculate the eigenvalues, and so when you have calculated the eigenvalues, so you can also look at are these levels degenerate, means that are some of the levels there that which are same energy. Okay, so let's look at this problem. So we'll try to be smart and we'll not use explicit matrices to calculate this thing. We'll use the eigenvalue equations. So let's just write this down. So you know there are these eigenvalue equations, so which are like s square. When acting on s and m, this kind of a kit, it will give you h bar square s into s plus 1. And you also know there is also this sz operator. When it acts on this sm kit, that will give you h bar m. So these are the two eigenvalue equations that you need to know. All of the other things are really simple. So I'll try to manipulate this operator so that I only get this kind of combination, only s squares and only sz. Okay, so I'll try to manipulate it. So how we can do that? So so here I'll just add a sz square. Okay, and I'll have to subtract the sz square again. So minus sz square. Okay, so there is additionally there is a minus sz square before, so that's why it becomes minus 2sz square. And then I am left with beta h bar sz. Okay, so alpha betas are just constants. Okay, so some constant, so which you don't know to which you don't need the value of. So then what it becomes is it becomes yeah, so it becomes s square. See, I have already obtained the s square combination, and minus sz square plus beta h bar sz. Okay, so I know all of these things, right? So in terms of what are the eigenvalues of this thing, I know all of these things. So what you want to calculate is, we want to calculate the expectation value. Okay, let's say on this state, on this s and m. Okay, so s comma m, and the operator that will sit inside is h bar square s square minus 2 sz square plus beta by h bar sz. Okay, so so we can actually use this eigenvalue equations, right? So this and this will act on it, this will act on it, it will give me some set of eigenvalues. So let's just do that. So s square's eigenvalue is h bar square and s times s plus 1. Okay, so sz and sz square will have the same eigenvalue. So this sz square eigenvalue will again become 2 h bar square m square, and then it will become beta h bar and h bar m. Okay, so this is the whole operator now, which I have reduced in terms of eigenvalues. Okay, so the operator is now reduced in terms of eigenvalues, and now let's just simplify this a little bit. So all of these are numbers, right? And the states they don't actually act on numbers. So the states will go through all of the numbers, and we'll have s comma m and s comma m. Okay, and the rest of the part will be h bar. So h bar square will cancel, and we'll have s into s plus 1 minus twice m square plus beta m. Okay, so we know that this combination, because all of the states are normalized and orthogonal, so this will become 1. Okay, so we are only left with this part. Okay, so this is the energy, right? So we have calculated the expectation value of the Hamiltonian. So this is the energy. Okay, so now for spin is equal to 1/3, s is equal to 3/2. So you can put this combination. So s times s plus 1, this becomes 3/2 times 3/2 plus 1, which is 3/2 times 5/2, 15/4. Okay, and so for s is equal to 3/2, can anybody tell me what are the values of m that can happen? So what are the values of m for s is equal to 3/2? So anybody? So okay, so the magnetic, yeah, go on. Yeah, exactly, right. So m, it will become minus 3/2 minus half 3/2. Okay, so total number of this magnetic quantum numbers will be 2 into s plus 1. Okay, so s in this case is 3/2. Okay, so it becomes 4. So like you will get only 4 quantum numbers. So you see that for a given s, right, for a given s you are getting 4 states. So and all, so right, so 4 states. So you can also write this m and s for this thing. Okay, so this is your energy. Okay, and we have not used any form of the matrices. We have just, so whatever operator we had before, so we had this kind of operator, we have tried to reduce this in terms of the eigenvalue, this s square operators and sz operators, which we know the eigenvalue of, and then we have simplified this thing using the eigenvalue equation, and we have obtained the energy. Okay, so these kind of problems are fairly common, and you can use this kind of tricks to solve this kind of problems. Okay, so let's do a few more. Yeah, so let's look at this problem. So this is quite interesting. So we'll again try to use this eigenvalue equations. Okay, so these are angular momentum operators. Okay, so this j, when traditionally when you write j, that means it has both the orbital angular momentum and both the spill angular momentum. So whenever we write j is basically L plus S. Okay, so but we don't need to go into that also. So this is very general. So now you are asked to calculate what is this combinations, what is the uncertainty in jx and what is the uncertainty in jy, and you find the product of it. Okay, so as you know, this uncertainty is given by this relation. So jx square expectation minus jx expectation square. Okay, so this is the delta jx. Okay, so to calculate, so let's first look at this jx average. Okay, so any idea that how should I approach this jx average? How should one calculate the jx average? So can anybody tell me any idea? What should we from where should we start attacking? this problem. Right. So right. So particularly in this case, if you write the jx, so like jx is given by this combination j plus I. Okay. So j plus j minus divided by 2. Okay. So there is some j comma m sitting here, and there is also some j comma m sitting here. So what will this combination will be? So what value will it give me? So this is j comma m. So let me take the half out actually. So j comma m, j plus, and sandwiching another side with jm, plus j comma m, sandwiching another side with j minus. So what will the combination be? So what is the values of this? Can anybody tell me what are the values of this and this? So this is a raising and lowering operator, right? So you might know this. So the raising operator, when it acts on this state j comma m, so that will give you some state. So there will be some number times some state, which will be m plus 1. So this is the raising operator. Okay. And for the lowering operator, so if we have some state jm, then it will give you some constant times j m minus 1. So it doesn't change the j quantum number, it will only change the m quantum numbers actually. So now any idea what will this expectation value become? What will happen to these expectation values? So let's try to do this algebra then. So so what will j do? So j will make this j plus 1. So it will make it m plus 1, right? Yeah. So and can we explain why it should be 0? And yeah, so you're kind of close, but let's try to see why this will be 0. So this is again, so I'm using the operator equations for j plus. Okay, so this is just a constant number. So let me just bring the constant number out. So you see that, so m and m plus 1, these are orthogonal, right? So because these are orthogonal, so if you take the inner product of this, that will become 0. So that's why this becomes 0. So the thing is, so j plus raises the m to be m plus 1, and when you take the sandwich with m, it doesn't give you back, right? So because of orthogonalities of the wave function, it will become 0. So similar thing happens here also. So it will make m to be m minus 1, but from the left hand side you are actually attacking with m. So because these are orthogonal, this will be 0. Okay. So always, it is always true that if you have only a expectation value of any raising or lowering operator or any creation annihilation operator kind of thing, the expectation value on a given state, it will be always 0, right? Because you have to conserve the number of things which is on the right hand side, then only you can have non-zero when you're taking the expectation value. Okay, so here the j plus doesn't conserve the m. So j plus increases the m by m plus 1, and j minus decreases the m by m minus 1. Okay, so that's why this will become 0. So similarly for jy also, for jy, so jy we can again write it in terms of these raising and lowering operators. For this case, it is given by j plus minus j minus by 2I. And in the same through the same arguments, you can show that this is actually 0. Okay. So again, you are getting the same kind of expectation like you are getting for the jx also. So this becomes 0. Okay. So now, okay, so we have got few components for this. So we know that jx average is 0, so its square is obviously 0. So now we are left with calculating the jx square and jy square, okay, to get this thing. So let's look at the jy square. So okay, so let's look at jx square in fact. So jx square. So jx square, I will again start from this the state j comma m, and so I'll sandwich j plus j minus by 2 square, right? So j comma m. So and we will find that which are the operators that will keep m same. Okay, only those operators expectation values will be non-zero. So let's first expand this j plus and j minus. So let's take this 1 by 4 outside also. So this will become j plus j plus plus j minus j minus. So you can write it as a square also. Then there will be j plus j minus plus j minus j plus. Okay. So now so like as I mentioned, so the recipe that which operators will keep the m same. Okay, so which will be the operators? So like I have this j square, right? So j square will increase the m by 2. Okay, so I will increase the m by 2 here, but I have the same m, and because these are m and m plus 2 states are orthogonal, so this will basically be 0. Okay, so same thing is true for j minus also. So j minus on the other hand will reduce the m by m minus 2. So we have m minus 2 on one side and m from other side. Then if you take the inner product, then it will give you 0 because of orthogonality. So only there are two other combinations. So what will it do? So see, j minus will decrease the m by m minus 1, but j plus will again revert it back. Okay, so this combination, this particular combination j plus and j minus, this expectation value will be non-zero only. Okay, so first of all you try to argue from symmetries or from whatever mathematical argument you can, you try to eyeball most of the things out. Okay, so you see this is 0, so this is 0 and this is 0. Okay, so we will have to only look at this j plus and j minus combinations. So 1 by 4 j comma m j plus j minus plus j minus j plus. Okay, so you can write this j plus and j minus, and you can try to so j plus and j minus has some matrix forms. We can try to evaluate it, but we'll do that later. Okay, so let's also calculate jy square also. So jy square expectation in the same way I'll write as jm, and then I will have j plus minus j minus by 2i square jm. Okay, so now let's expand it. So because of I square will give you minus, so I will have minus 1/4 outside. Okay, so then we'll have jm, and similarly we'll have j plus plus j minus minus j. Okay, so plus or yeah, it will be minus j plus j minus and minus j plus. Okay, similarly like we argued last time, here also this will go to 0 and this will also go to 0. Okay, so we are left with, so there is a minus inside, so I'll take the minus common and the minus outside will cancel with that. So j comma m, so j plus j minus plus j minus j plus j comma m. So you see that these two equations, so this and these two equations, these are exactly same. Okay, so I mean, so this was just to show you that jx square and jy square are same. Square average is same as jy square average. Okay, but so now I have showed you that okay, these are actually same, but what about the values? What are the values when I take a expectation, right? So now to answer that, we'll again be a little bit smart. Okay, so as you know, like j square is given by jx square plus jy square plus jz square. Okay, so I know this eigenvalue equation of j square and eigenvalue equation of jz. Okay, I will try to reduce these expectations in terms of those things only. So how do I do that? So like jx square expectation is, let's write it like this, half of jx square plus jx square. So now because jx and jy, these squares are same, so I'll write jx square average plus jy square. Okay, and you know I'll do what? I'll additionally add a jz. Okay, and I'll also have to subtract that part, so jz square. So the first three terms actually give me j square, and the last term gives me jz square. So like as I said, I only know eigenvalue equation of these operators, so I'll try to evaluate these operators only. So expectation of this and expectation of this. So now if you just put the eigenvalues, Okay, so let's just put the eigenvalues directly. So it becomes half j into, okay, so there is a one h bar square j into j plus 1 and minus h bar square m. Okay, so basically this is the jx square. Okay, so now you know jx square, which is same as jy square expectation. So you plug these things back into this this relation. Okay, into this relation. Okay, and you will get the this delta jx and delta jy. Okay, so was this okay? Is this okay? I mean, is there any doubts? Please ask me. All right. So all right. So there is one additional problem that I want to talk about. So okay, so let's look at this problem once. So this is the last problem for this session. Okay, so now we are talking about spin 1. Okay, so for spin 1, this angular momentum operators are given by jx, jy, jz, which are like this 3x3 matrices. Okay, so when you look at it, you can ask me that how do you get this matrices. Okay, so are these come out of the blue? I mean, how do you get this, right? So basically you know the this matrix elements of all of the angular momentum operators, right? So you know that jx is given in terms of j plus j minus by 2, and jy is given by j plus minus j minus by 2i. Okay, so you know this. So basically you know the matrix elements of j plus and j minus individually. So you can calculate the matrix elements of j plus and j minus, and you can just sum them up to calculate jx, or you can just subtract and divide by 2y to get the jy. Okay, so that's how you basically get this kind of matrices. You can try this out for, let's say, larger matrices. Let's say S is equal to 2. Okay, so in that case it will become a 5x5 matrix. But these are very, very simple. Like you have, so this is just like some algorithmic thing. So you just use that formula of this matrix elements of j plus and j minus, and you just build the whole matrix from this. Okay, so now if these are the given matrices. Okay, so first of all, so the first question is, what are the eigenvalues of this jx Okay, so this is the thumb rule that whenever you have any spin s, so any component of spin you measure, like x, y, z, any component you measure, so you will only find there are 2s plus 1 values. Any component, it might be x, it might be y, it might be z, right? So it depends on you, what you call x, what you call y. So what you call x, I might call it y, but the physical measurement that I do on that spin will not change because of that. Okay, so just from this simple argument we can say that, okay, there are actually 2s plus 1 eigenvalues. So for spin 1, so we should get actually 3 eigenvalues. So these 3 eigenvalues are nothing but minus h bar, 0, and plus h bar. Okay, as simple as that. So we don't need to solve the eigenvalue equations to get the eigenvalues, but to get the eigenvectors we need to solve this eigenvalue equation actually. Okay, so let's first solve the eigenvalue equation. So let me just copy that there. So in case you don't know this this set of notes which I'm just doing in front of you, this will also be available to you. All right, so jx, so what is the eigenvalue equation? So let's say jx a b c, this is my eigenvector, is given by e and a b c. Okay, so I want to find the abc, I want to find the eigenvector, right? So let's try to find the abc. Okay, so let me put the this jx first. So jx is 0 1 0 and 0 1 0. Okay, so I can bring the e to the left hand side, then it becomes so okay, so let's actually do one. Okay, so let's just keep it like that. Okay, so okay, so I'll bring the e on the other hand side, so then it will become minus square root 2 e by h bar 1 0. So 1 minus square root 2 e by h bar 1 0 0 minus okay 0, this is 1 minus square root 2 e by h bar. Okay, so you see I have taken common this total h bar by square root 2. So because e didn't have it, so I have to divide it with the same thing. Okay, and this times a b c. Okay, so I want to solve these three linear equations. So what are these three linear equations? So let me write minus h bar times a plus b is equal to 0. So this is my equation 1, and then there is a minus square root 2 e by h bar b plus c. So this is from the second row of this matrix, and there is the last one, which is b minus square root 2 e by h bar c is equal to 0. So this is the third one. Okay, so we have to solve these three linear equations. So the thing about solving the eigenvector is like you don't have to get the exact values of a b c, because you have some degree of freedom. So there is the normalization, that freedom you have. So if you find the ratio between a, b and c, that will do the job. Okay, because at the end of the day you will have to anyway normalize the whole wave function. So let's try to do that. So from 1, okay, so from 1 we see that a by b is given by h bar square root 2 e. Okay, so this is from 1, and so from 3 we see that b by c is given by square root 2 e by h bar. Okay, so I know the ratio between a and b to c. So how do I get the ratio between a and c? So I'll just multiply these two equations. So ab times bc is equal to h bar square root 2 e and square root 2 e by h bar. So these things actually cancel and gives you 1. So a and c, this is 1. Okay, so I know now all of the ratios. So a by b is h bar by square root 2 e, a by c is 1, and b by c is square root 2 e by h bar. Okay, so I don't actually need this part. So now let's say I am choosing my a to be 1. Okay, so if I choose my a to be 1, then what do I get out of these two equations? So now b becomes square root 2 e by h bar. Okay, and c becomes 1. So now with this information, can I construct the eigenvector? So I have chosen my a as 1, right? So because I have chosen a as 1, my c also becomes 1, and then the b, we are left with square root 2 e h bar. Okay, so now this is your state, this is your eigenstate. Okay, so now you can plug in the values of e. So let's say when e is minus h bar, so then let me write it as this minus state. Okay, so this is 1 minus square root 2 1, and if you normalize it, you get a half factor. Okay, so because you have to always normalize it, right? And then when e is 0, so then you get 1 by square root 2 and 1 0 1. Okay, so the middle factor becomes 0. When e is h bar, then you get plus state, so which is 1 by square root 2, 1 by 2 actually, 1 square root 2 and 1. Okay, so these are all of the eigenvectors of all of this Sx operator, Jx operator actually. Okay, so now when you have obtained the Jx operator, you can calculate this this Jx. Okay, so Jx average, Jz average, Jz square average, and you can also calculate the delta Jz. Okay, so you can do same for Jy, right? Because you know all of the state, and you are asked to do the calculation for the Jx is equal to minus h bar state. Okay, so that means you have to calculate the expectation values about this state. Okay, so you will calculate Jz minus, you will calculate Jz square minus, and you will also calculate this delta Jz. Okay, for this minus state, and do the same calculation for Jy as well. Okay, so now when you are done with that, so let's just do this last part, okay, which is actually quite interesting. So now, so let's say I am given a state, okay, I have given a state psi, okay, so which is a weird looking state, right? So now I am asking you, if I measure Jx as plus h or minus h or 0, what is the outcome, what is the probability of the outcome? So what is the probability that I will have plus h bar if I measure the angular momentum along x-axis? So what will be the probability of getting 0, this angular momentum about x-axis? What will be the probability of getting minus h bar, these states? Okay, so to do that, what we will do is, so let me first copy this state. So this kind of question, to solve this kind of question, so the probability of finding Jx, so the eigenvalue Jx, when I am writing a small Jx, so this is the eigenvalue I am talking about, as minus h bar. Okay, so minus h bar, that corresponds to state minus. Okay, so what first job is to calculate the overlap. Okay, so this is the first job you should do when you are asked this kind of probabilistic questions. So you should take the overlap first. So the overlap, let's write it. So half, we have 1 minus square root 2, 1, and then there is a dot product with the psi, square root 3, 2 square root, so minus square root 3 and square root 3, there is 1 by 14 additionally. So what, yeah, right, yeah, thanks for noticing, right? So then it becomes minus 3 and minus 2 times 2 and plus square root 3. Okay, so square root 3 that cancels, and then I am only left with minus 4 by 2 square root 14. Okay, so this is, I will cancel the 2 from top and bottom, so 2 by square root 14. So this is the overlap, right? So this overlap doesn't give me probability. What gives the probability? The overlap's mod square. So the probability is given by minus and psi mod square. So this is you will see that this becomes 4 by 14, so this is 2 by 7. Okay, so this is the probability of getting of when you measure this angular momentum around x-axis, along the x-axis, this is the probability of measuring a minus h bar. Okay, so you can again do when the Jx is 0 or Jx is equal to h bar. So you will do the first, you will calculate the overlap, and then you will take the mod square. Okay, so mod square will give you the probability of finding the particle in that particular state. Okay, so you can calculate for this too. I'll leave this for you. Okay, so this was basically it. So any questions up to this point? Okay, if not, then we'll finish today. Okay, so then I'll see you next week. Okay, have a good weekend then. Okay, yeah, okay, thank you for joining. Okay, I'll see you later. Yeah.